Hello everybody, my name is Andrzejczak, also known as Chopin. I'm a generalist with a strong programming background. 9 years of industry experience, and my main focus of interest is both tech art and game design. My current role is a technical director at Black Drakkar Games. We provide work-for-hire services to other computer games companies. You might have played one of the games we work on called Fort Solis, which was released last summer. Here you can catch a glimpse of the games I worked on. Unfortunately, some of them are still under NDA. I've developed games for several platforms, including PC, VR, mobile VR, Nintendo Switch. Today, I'm going to talk to you about Gaussian splatting rendering technique. Okay, so what is a 3D Gaussian? Well, let's start with 1D Gaussian. It's simply the bell curve. 3D Gaussians are a generalization of 1D Gaussians in a higher dimension. Essentially, they are ellipsoids in 3D space with center, scale, rotation, and softened edges. Additionally, each 3D Gaussian contains the data about view-dependent color and opacity. It's stored in a form of spherical harmonics, which I'll briefly explain later. Okay, so in other words, to make sure that you understand, it's a new kind of a primitive. So you start from a sphere. You can squeeze it, you can stretch it, and it already contains information about its color and opacity from every perspective. For example, it could be an opaque green sphere seen from the top, or semi-transparent red if seen from the bottom. This Gaussian splatting buzz started last year when a group of computer scientists from France and Germany published a paper at SIGGRAPH about utilizing 3D Gaussians for real-time rendering. They compared the results with other techniques. For example, you might have heard about Nerf. It's a short for neural radiance fields, which are used for view synthesis. This Nerf trains a separate neural network for a given scene, and these network weights are used to recreate the scene in the virtual environment. The training requires numerous photos taken from various angles. In this bike in a park scene, classic Nerf requires 2 days of training. And then rendering a single frame takes 14 seconds. Instant GPT, a much quicker version, but with slightly less fidelity, requires 7 minutes of training and achieves a frame rate of 9 FPS, which is suitable, I guess, for GIFs, but not for interactive scenes. In contrast, 3D Gaussian splatting approach delivers astounding results. 135 FPS with a training time of just 6 minutes. For a slightly more faithful representation, the training time increases to 51 minutes, but it still achieves a decent frame rate of 93 FPS. You may go to their website at GitHub and download the code, paper, training data, models, and rendering software. Okay, by the way, I'll provide all the links with references at the end of the presentation. In standard computer graphics, we use rasterization with triangles that are often connected with one another. 3D Gaussian splatting models are also rasterized, but with individual, unconnected Gaussians. Okay, so this is how it looks in motion. Here I'm using the rendering software from this GitHub page I mentioned. Controls are a bit tricky, so I apologize for a weird camera motion. Take a good look, especially at highly detailed leaves and curly strands in the decoration. What is also worth noting are the reflection of the glass. This is this example of view-dependent color and opacity. When I dig the camera inside the model, you might see the individual splats that make up the scene. Okay, you might wonder how such scene is created. To train the model, they use stochastic gradient descent techniques for optimization, taking full advantage of GPU and CUDA power. There is no AI, no neural networks involved, unlike in the case of Nerf. Okay, so I encourage you to read the whole article for the details. It's heavy technical and it's not an easy read, but yeah, they explain everything. Here I would like to show you one part of the reconstruction process. Say we have a shape marked with this green line. It's like a part of the photo, the grand truth, and a nearby Gaussian splat. It's not covering the whole shape, so the algorithm clones it. Then the optimization continues, and these splats are squeezed, rotated, so that they resemble more the final shape. And in the bottom case, it's like this splat is much bigger, so it has to be splitted, and then optimization continues, and we reach the same effect. So both passes work in tandem. So how to place such Gaussian into Unreal? Fortunately, there is a plugin available. Unfortunately, it requires a purchase, and there will be no discounts. The author created a tool that writes the Gaussian splatting data into textures, which are read by the Niagara particle system and its shader. It's a kind of emulation, as sprites composed of two triangles are necessary to show the appropriate projection of splats, but it works very well. However, there is another plugin that supports both Nerf and Gaussian splatting, which is free. It works in the same manner, so I recommend trying this one first if you want to simply test out the technology. However, if you are looking for the best quality, unfortunately, the first plugin is noticeably better in terms of rendering. Okay, anyways, here is the bike in a park scene imported to Unreal Engine with the paid plugin. As I mentioned, splats are rendered with Niagara particles. Now I'll show you the individual splats. So that's the standard view. Here, I place the UV coordinates in the emissive input of the material used by the particles. The larger splats are likely responsible for a bit hazy look of the scene. This is the transparent version, and an interestingly looking alpha composite one. Now I'll show you a little hack to see the true face of Gaussians. I placed an additional camera, and its view is visible here. I'll be moving the main camera, and all splats will be facing only its direction, so the direction of the main camera. So look here. They are trying their best to look good for the main camera. If you want to create your own models, you have several solutions. You may try Polycam, which has a rich gallery of ready-to-download models. Unfortunately, you have to pay $18 per month to unlock the feature of creating your own models. There is also Luma.ai, also with great examples of other users' work, like this one. On this website, the pricing is different. It's $1 per model. There are also mobile apps like Kiri for both Android and iOS, and Scaniverse, which is an iOS exclusive. Here is a clip by Olli Huttunen, which shows how Scaniverse works. What is nice about this app is that it shows in real time how the capture works. Afterwards, you may train the model locally on your phone for as many iterations as you want, so you don't have to send it over the internet. There is also an offline and free solution. The software is called PostShot, and any moderately good PC will work just fine with it. You don't need a Bitcoin mining rig. PolyShot works like this. All you need to do is press a button and drag and drop photos of the space you want to model with Gaussians. Make sure the photos are taken with different camera angles. For example, here I took 69 photos of a figurine depicting one of the characters from Steins Gate game. After 30 minutes of training, I didn't see much of improvement with next iterations, and I was happy with the results, so I decided to stop here. When I was filming this clip to show you the results, I suddenly heard this voice. It was at this moment he knew. I realized I had forgotten to tidy up my room, and I wouldn't want to show you such a mess. But repeating the whole capturing process would be boring and tiresome, so I decided to try cleaning up the model instead. So there is a super cool web-based free program called Super Splat. You simply drag and drop the model file, and you can use several editing tools. Okay. So yeah, these scans will look like this. And the figurine is hiding somewhere in the middle. To extract such a model, the easiest way is to use Sphere tool, which you can see here. Use appropriate scale and apply selection. Then actually you should use inverse selection and delete all the splats, which I'm doing here. Then you can try to refine the model even more and try to delete the remaining splats you don't want to have with a brush tool. Yeah, this video is, I think, 10 minutes long, so. But let's move on. This is the final result, imported back to PolyShot. Notice the reflections and fine detail of tiny elements like cables and sockets. There are no textures here. And here, the model was imported back into a basic level of Unreal Engine 5. I must admit it looks slightly worse than in PolyShot, but the result is still quite impressive to me. Okay, I must emphasize again that this is a Niagara-based solution. Anything that works in the standard Unreal Engine rendering pipeline with Niagara sprites will also work with these models. As for the performance, it's comparable to moderately heavy GPU-based Niagara systems. For much small props, it's super fast. For room-sized ones, it's obviously slower, but it's still very playable. Okay, there is one disclaimer. You might remember that the model imported for cleaning in SuperSplat had an odd rotation and was upside down. There is an option to change the rotation both in PolyShot and SuperSplat, but I do not recommend using it. Saving file with changed rotation somehow disrupts the data. I don't know about the reason, and I contacted both teams. Maybe they'll know what's happening. Nevertheless, you may always apply the desired rotation in Unreal Engine, and it will look fine. The paid plugin for importing Gaussians into Unreal allow us to select several options, one of which is the spherical harmonics degree. So spherical harmonics are a mathematical tool that encodes the data about color and opacity, and it is stored in polar coordinates. Spherical harmonics can be thought as Fourier transform, but in 3D dimensions. And the higher the degree of spherical harmonics, the higher the resolution of the data. A degree of 0 means no view-dependent color and opacity at all. So for a moment, I thought that the previously mentioned loss of quality caused by rotation might be linked to losing spherical harmonics data. However, if you compare the left and the middle picture, that doesn't seem to be the case. Interestingly, you don't have to use photos of real environments. You can easily create Gaussian splatting models using screenshots of your virtual scenes. You might wonder why Voldemort is standing on a colorful floor. The algorithm for creating Gaussian splatting scenes needs good reference points for determining camera transforms. When I tried to capture Voldemort floating in the black void, the algorithm simply failed. When I used tiling texture, I ended up with 2 Voldemorts. One, or I guess 2, maybe too many. So here I took 68 photos, screenshots. Obviously, I've automated the process. And finally, here is a Gaussian splatting of Voldemort, featuring a small tech demo. I was inspired by the visual effect of this character death in the movie. Now I would like to showcase more examples of clever uses of Gaussian splatting. When I was browsing the Polish Polycam library, I encountered this friendly guy. Remember, Gaussians store data about color and opacity depending on the view angle. No one said the model has to maintain the same pose during capture. Besides the change in facial expression, I wonder if you noticed that his eye were smoothly following the camera. Here is another interesting example. Here you can see a ghost wall effect. And this actually shows up during training process regularly, every couple of thousand steps. And if you stop the training on such iteration, you can achieve similar result. This last example was created by Olli Huttunen. I recommend watching his channel. He's doing very great stuff. For instance, he recorded an entire floor of an underground parking lot with a camera. He used a 360 camera. Polycam managed to recreate the scene with 8 separate video clips in good quality, demonstrating that this technology can be used for both detail, small detail, and also large environments. I think his training time was over 1 day, but yet this space was huge, like 4 times this room. Okay, so I wondered about another effects I could create with Gaussians, and this is what came to my mind. Okay. Here is another version. Instead of a lamp, try to imagine a gun a player could use to burst out parts of the level with every shot. Okay, So in this lecture description, I mentioned there is also possible to create Gaussians with AI. It's true, but not entirely. For example, the Dream Gaussian GitHub page provides an implementation of this approach. Once you download the code, it works offline on your PC. They provide examples of 3D Gaussians generated from short prompts like a campfire or an ice cream. However, these images are small for a reason. If you zoom in, you'll realize that they are very blurry. And yeah, I would recommend to either wait for some updates or search for better tools. What's interesting, they also offer the ability to create a Gaussian out of a single image, like this one. So the output is here. The AI had to infer how the back should look like just from the front image. So the hair looks quite adequate, but the rest is, well, not quite production ready. But keep in mind that the AI gen field is so dynamic that there might already be much better generative tools that simply flew under my radar at the time of preparing this talk. As we approach the end, I would like to show you two more things. There are some great groups out there working on 4D Gaussians, which incorporate temporal variance, essentially animation. Just take a look. Shadows are also working. There are new tools supporting Gaussians every week, so be on guard. Here is the tool developed by Yoshiharu called Godzilla Pro Editor. It's web-based, and at the moment you need to wishlist to get an access. He developed an interactive 3D Gaussian segmentation system powered by AI. This software allows you to select like solid objects. You can erase them, you can clone them, you can rotate them. Obviously, there are some limitations, but it's still work in progress. If you'd like to explore the topics I mentioned during the talk, here are the important links. As for the presentation, it's the end. Thank you for being here, especially at this late hour. I hope you enjoyed the talk and might consider trying out this new tech. If you have any questions, now is the time.
Hi, thank you for the talk. Do you know if there are any solutions for implementing collisions to those Gaussian splatting in Unreal?
Oh, I actually saw such tool. I forgot to add it, thank you. But it looked very complex. So imagine complex collision in Unreal, and it looked very similar. So I guess it could work, but it will be unoptimized.
Okay, thank you.
No more questions, I guess. Everyone is tired. Okay, so thank you again for listening. Have a safe trip back home. Thank you. Bye.